Hi, I'm Ashley and I'm going to be talking to you about my project as part of my PhD at the University of Leeds Centre for Doctoral Training in Molecules to Product. The title is All-cellulose composites, fast fashion to smart materials, and in a nutshell it's about looking at developing functional, easily recyclable materials using end-of-life clothing waste. We generate a lot of waste. In 2018, just over 26 million tonnes of waste was generated from households in the UK. The United Nations Sustainable Development Goal 12 relates to responsible consumption and production. This involves using natural resources more responsibly and reducing waste generation through recycling and reuse. Our efforts in recycling have made considerable improvements over the last 20 years to the way we manage waste, but there's still a large amount of unrecycled waste destined for landfill or incineration. Why is this? Well, this depends on the kind of waste being discarded and the viability of the recycling route, and this can vary among product types. With the growth of fast fashion over the years, more clothing is being discarded, sometimes after being worn only a handful of times. Although it is possible to recycle end-of-life clothing, the process of separating fabrics to fibres can be energy intensive and disruptive, and it can lead to recycled fibres with a loss of strength and quality. This means they're often downcycled to lower grade products. Breaking down materials into their individual components is easier for some materials than others. Although many plastics can be recycled, there are some polymer-based materials that can't. Fibre-reinforced plastics, for example, have additional components added to improve their properties. This is known as a composite material. Composites are materials produced from two or more dissimilar components, such as a fibre and a polymer. These components remain as distinct phases within the composite structure as a matrix and a reinforcement. This means favourable characteristics can be combined in one material, such as high strength or the ability to withstand stress without failing. In order to recycle them, the different components within them need to be separated, and this can make the process complex and costly. So what if we could make use of end-of-life textiles so that they avoid becoming waste, and at the same time produce new sustainable materials that can be recycled more easily? This is where my project comes in. A large amount of fabrics used to make clothing are made from cellulosic fibres such as viscose, hemp, flax, and one of the most popular fibres used in clothing, cotton. Cellulose is a biopolymer that originates from plants, bacteria and algae. Strong hydrogen bonds between the cellulose units lead to the formation of microfibrils, which have been found to have excellent tensile properties that can match that of steel. This biopolymer has the potential to bring strength to materials, and I'm interested in its use in the preparation of all-cellulose composites. Here, both the matrix and reinforcement phases are formed from cellulosic material, resulting in a composite made from components that are chemically identical, making them easier to recycle than traditional composites. Cellulose fibres can be partially dissolved using ionic liquids. On regeneration, the ionic liquid is removed, leaving a matrix formed from dissolved cellulose, and the undissolved portion remains as fibres acting as the reinforcement. One of the challenges faced with this technology is the ability to produce thicker composites, which would expand their applications. A process has been developed at the University of Leeds that can achieve such thicker materials with excellent properties. Ionic liquid is introduced to the layers of a cellulosic fibre-based fabric, and an additional layer of cellulosic film is added between these layers. This encourages an additional matrix to be formed, which helps to increase the adhesion between the layers and allows enough undissolved fibre to remain in the composite, which provides strength. This overcomes the issue of delamination, which is common with layered materials, where the strength of adhesion between the layers is not sufficient to hold the layers together. With this method, we can use fabrics instead of fibres as a source of cellulose for the composites. This makes use of end-of-life textiles, eliminating the need for mechanical separation processes. I'm going to investigate the properties that can be achieved in all-cellulose composites using different types of cellulosic fabrics present in clothing waste. The key themes underpinning my research are focused around composite functionality, recyclability and industrial viability. Can these materials make suitable alternatives to those that are harder to recycle? How do different weave types influence the structure and mechanical properties of these materials? Can we discover how different forms of cellulose respond to dissolution and how they differ from each other? Recyclability is also hugely important. Can it be done? How can it be done? And how can we optimise this for ease of recycling? And finally, industrial viability is key. I will look critically at all aspects involved in the process, including processing conditions, solvent use and recycling, as well as a cost analysis to assess economic viability. By considering the full life cycle of a product, we can design a process and a material that will enable the product to remain in a circular economy. This will make use of clothing waste, reduce the amount of virgin materials required to make new products, and it will move us forward in the development of a circular economy.